We're digging through research today on something, well, kind of invisible. The engineering that decides how long your stuff actually lasts.
Right.
And today, specifically, we're breaking down garment construction. The science, really, behind why your clothes sometimes just fall apart.
Yeah.
Or why some things last forever.
Yeah. It's a design challenge most people probably don't even think about. We see a shirt, we see the color, the fabric maybe,
Mm-hmm.
but someone developing that product, they see stress points,
Mm-hmm.
potential failures waiting to happen.
That's exactly it. We've got a stack of sources here all about garment durability. And our mission really is to give you that shortcut, to understand how designers try to make clothes last longer.
Right.
We want to move past just saying, oh, that's cheap, and get into the actual engineering, the specific challenges they face, like every time they stitch two pieces of fabric together.
And we really should start with what garment stress actually means, technically speaking. So we're talking about mechanical forces, things that cause localized failures, like tearing, ripping,
Sagging.
snagging, or just constant pulling. Tension. Understanding this stuff is crucial, especially for clothes that get a lot of action.
You mean like activewear?
Exactly. Activewear, work clothes, anything for kids, really. The lifespan of that item, whether the customer is happy, it all comes down to predicting and handling the stress.
Okay, let's unpack that then. If durability is engineered, what actually determines how much stress, say, this shirt is under? Because my old flannel shirt feels different than, I don't know, a backpack strap.
Well, it's never just one single thing. It's always a combination, a convergence of inputs. Designers really have to juggle like 4 key factors. These decide how severe the load is on any given scene or piece of fabric.
4 factors. Okay, what's the first one? Let's start with the material itself. Fabric's type.
That's the absolute foundation. It's about the fabric's inherent properties, its DNA, strength, elasticity, weight, even density. And our sources really emphasize that link between density and strength. So a tightly woven cotton, think canvas, or maybe a heavy twill.
Okay.
That's got way more resistance to tearing than, say, a loose jersey net.
Yeah.
Just because the fibers are locked together more tightly.
But wait, that brings up a conflict, doesn't it? If woven cotton is stronger, why is so much activewear, tech gear, made from knits, which are more flexible? Are they choosing weakness?
That's the classic design trade-off, right? You're sacrificing that ultimate tear resistance.
Flexibility.
For comfort, knits are great at absorbing stress. They stretch, they bounce back, they spread the load out. Woven fabrics, they resist stress. They hold their shape until pop, they hit their breaking point and fail suddenly. So the designer has to ask, do I need absorption or do I need resistance?
Fascinating. Okay, factor number 2. Garment intended use. What the clothing is for.
Absolutely.
Yeah.
The purpose completely dictates the kind of strain it's going to face.
Yeah.
If you're designing something for heavy use, think gym clothes, construction gear, play clothes.
Right.
You have to anticipate extreme movement, lots of stretching, rubbing, friction. You basically need to build in a safety margin for every single seam.
Makes sense. Then we get to the factor that, well, most of us feel every morning, garment fit.
Yep, this is the tension from us, the human factor. Tight clothes generate way more constant internal stress right on the seam.
So that pulling feeling across your back.
That's not just discomfort. It's physical tension.
Yeah.
Actively working to pull the threads, pull the fibers apart all the time.
And looser fits.
Well, they have less of that constant tension, but, maybe they snag more easily because there's extra fabric flapping around.
Yeah.
Or they might face more abrasion.
Okay. And the last one, the 4th factor, is pure anatomy. Seam location, where it is on the body.
Exactly. Some areas are just naturally high risk. Why? Because they're right next to joints that are always bending and moving.
Like elbows, knees.
Elbows, knees, the crotch area, definitely. The armhole seam where the sleeve joins the body. Shoulders, too. These spots get constant bending, pulling, friction. You know where the problems are likely to be before you even start.
So if we connect all this, garment stress isn't random. It's predictable, really, based on materials and how humans move, the weak spots. So how do designers actually deal with this? They can't just make everything out of super heavy canvas, can they? That would be awful to wear.
Right, and that's where the engineering toolkit comes in. Over-engineering everything makes it stiff, heavy, expensive. Nobody wants that.
So
product developers use a system. They classify areas into 3 levels: high, medium, and low stress.
okay, different levels of worry.
Exactly. And this lets them customize the construction, put the reinforcement only where it's really needed. It's about using the right technique in the right place.
Let's dive into that classification, starting at the top, the high stress areas. The big leagues.
These are the zones that take the most significant, really concentrated strain. They need seriously robust construction. We're talking points where failure is, well, catastrophic.
Not just a loose thread.
Oh no, we mean seams completely splitting open, zippers busting, pockets ripping off.
Ouch. Okay, give us some specific examples. Where are these high-stress danger zones?
Think about the structural core. Shoulders, especially shoulder straps, if they're carrying weight, like on a bag or overalls.
Right.
Tight necklines you pull over your head constantly.
Yeah.
The absolute critical point where seams meet in the crotch.
Yeah, that's a classic failure point.
Totally. Pocket openings, especially on jeans or work pants where you're always shoving your hands in. And any kind of closure under tension, like a zipper fly, these spots have to be built tough, over-engineered, essentially.
Got it. Okay, moving down a level. The medium stress areas. What's happening here?
Here you've got moderate tension, moderate movement. So the construction needs strength, yes, but also flexibility. You don't want it to feel like armor.
So it needs to move with you a bit.
Precisely. Failure here is usually seams splitting or maybe gaping open, not that sudden, dramatic tear you get in high-stress zones.
These are kind of the workhorse areas then.
Yeah, that's a good way to put it. Think about side seams. They stretch when you sit down or twist.
Okay.
Open necklines that need to drape nicely. Most waistbands that have elastic. The main seams down the sleeves. They move, sure, but the tension isn't quite as focused as, say, right at the elbow joint.
Right. And finally, the easy ones, the low-stress areas.
Well, easy in terms of tension. These spots see minimal stress or movement, so the main focus shifts away from brute strength. Towards aesthetics, mainly. And crucially, just stopping the edges from fraying or falling apart over time. The problems here aren't rips, but more like messy seams, edges unraveling, maybe stitches coming loose after washing.
So it's about neatness, longevity in a different way.
Exactly. Think about most pant hems at the bottom, or decorative seams that aren't holding anything together. Open sleeve cuffs. Here, the designer just needs a finish that locks down that raw fabric edge so it doesn't degrade.
What's really interesting, though, is what you hinted at earlier. This system isn't totally rigid. A medium stress area on one shirt could be high stress on another, right?
That is the crucial point.
Yep.
Absolutely. These levels are just guidelines. You have to look at the specific garment. What's the fit like? What's the fabric? What's it actually for?
So like a side seam on a loose, flowy dress.
Low stress.
Yeah.
Probably. But take that exact same seam location on, say, super tight leggings or tailored trousers. Suddenly jumps up to medium stress, maybe even high stress, because that constant tension from the tight fit changes everything. The designer has to make that call for every single seam individually.
That makes perfect sense. And it leads us right into the practical side. We know where things might fail, so what are the actual tools, the engineering solutions designers use to make those weak points stronger? How did they build what you called strong seams?
Okay, yeah, the toolkit. It really starts with enhanced stitching, using techniques that basically make the seam itself more secure, better at handling the load.
Like double stitching. We see that on jeans all the time. Triple stitching sometimes.
Right. That clearly adds strength. You're literally adding more lines of thread to break. And it often looks good, too. Becomes a design feature. And especially for knits, like performance wear, flat lock stitching is everywhere.
Why that one specifically?
It's super durable, but it also lies flat against the skin so it doesn't chafe during movement. And it holds stretchy fabrics really securely. But maybe the most subtle trick, one you might not notice, is just controlling the stitch length.
Making the stitches shorter, why does that help?
It's just physics, really. A shorter stitch means the needle goes through the fabric more times in the same length of seam.
Okay.
So it spreads the stress out over more points, more little intersections of thread. If you have long, loose stitches, the strain focuses on just a few points. Shorten the stitch length, and bam, you've made it significantly stronger without adding any bulk.
Clever. Okay, so beyond the actual stitches, you mentioned edges, fraying. That brings us to seam finishes.
Yes, this is key for preventing that slow decay, especially in those low and medium stress areas. You use finishes that properly enclose or secure the raw edge, like bounded seams where the edge is wrapped in another piece of fabric.
Or serging, that overlock stitch you see inside most clothes.
Exactly. Serging or overlocking trims the edge and wraps threads around it. The whole point is to trap those raw edges so they physically cannot fray and unravel over time and through washing.
Got it. And for the really high-stress spots, sometimes you need hidden help, right? You mentioned structural support, like stay tapes.
Ah, yes. Stay tape. Sometimes it's clear plastic tape, sometimes a non-woven fabric strip. It gets stitched or even laminated right into the seam allowance, usually hidden inside.
Where would you find that typically?
Shoulders are a classic example, especially on knit tops or blouses that might otherwise stretch out of shape. It stops the fabric from distorting under tension, like from the weight of the sleeve or just gravity. It adds stability without stiffness, keeps the garment's shape.
Okay. And then the heavy artillery, strategic reinforcement, bar tacks, rivets. We see these all the time, but maybe don't know what they're doing.
These are the real defenders against tearing at super high stress points. A bar tack is that little rectangle of dense zigzag stitching.
Like on the corner of a jeans pocket.
Exactly. That's its job. To lock that corner down and stop the pocket from ripping away when you jam your hands in or catch it on something, it takes that sudden pulling force.
And rivets, the little metal studs.
Same idea, but even stronger. Usually metal. They provide ultimate reinforcement where seams meet or face extreme stress. Again, think jeans pockets, the base of a zipper fly, maybe where a handle attaches to a heavy bag. Maximum security.
Wow, okay. So bringing this all together, what does this mean for us? You know, the person buying and wearing the clothes, how does this knowledge help?
Well, it changes how you look at quality, doesn't it?
Yeah.
Instead of just glancing at the price tag, you can actually start to, well, assess the construction yourself. Like, if you're buying workout leggings, you now know to look for flat lock stitching on those side seams. Maybe check if the stitch length seems reasonably short.
Oh.
Buying jeans, look for those bar tacks at the pocket corners and the bottom of the fly. Are they there? Are they solid? You move from just asking, is this good quality? To a more technical question. Okay, did the designer actually reinforce the high stress points properly for how this garment is meant to be used?
That really is the key takeaway, isn't it? Being able to spot quality construction where it matters most. So, just to recap, we talked about classifying stress, high, medium, low. Understanding those four factors: fit, fabric, use, and location, and then applying the right tools: bar tacks, stay tape, double stitching, even just getting the stitch length right.
Exactly. And by addressing these stress areas properly, designers aren't just, making a shirt, they're actively engineering against failure. It's about durability. That structural integrity is often totally invisible.
Until it fails.
Precisely. Which is why knowing about these techniques helps you understand what makes for long-term satisfaction with your clothes.
So here's a final thought for you listening. If clothing durability really does hinge on construction that's tailored to movement and tension, take a look at your favorite, most worn piece of clothing right now. Which seams on it are working the hardest? Maybe that crotch seam on your go-to jeans, or the shoulder strap on the bag you use every day. What specific engineering solution is actually holding it together? Or maybe what's missing? That's something to think about next time you get dressed.